Welcome to another edition in this series of videos, kind of redoing Professor Lewin's 802 physics videos on mostly electricity and magnetism. And I guess before I play this next video, kind of go over a couple of points. My channel is called Draft Physics, and sometimes you have to make some changes to which you thought was a good model, and part of the problem is they don't have a model of the mechanism. They just really are dealing with effects and not really much in terms of explaining the progression of causes through the system, the mechanism of creating charge and having charges affect other things and charge them and create further effects that create further charge effects, and so on and so on. So they don't give you much to much of an example to compare different models to. But the basic idea, I would argue, is that atom can be in three states. Let's just say, for the fun of it, some of the atoms. Some atoms don't do this state thing. They have one form and that's it. So the atom can have, let's just use 3 as the number here. It can have 4 electrons, or it could have 5 electrons. And we're just talking about usually the outer rings of the atom. So these would be the types of atoms, so to speak, that could be configured. So you can think of this square one as the neutral. Yeah. Thank you. I appreciate that. Forces of nature helping. Alright, so you have these 3 forms of the same atom. And so this would be your negative ion. This would be your positive ion. Well, actually, it'd be the other way around. This would be your negative ion, and this would be your positive ion. So this one has kind of the obvious appearance of being more red heavy. This one is more black or brown heavy. In this case, brown, but it doesn't really matter. So you could sort of understand that what's going to be happening in reality is that a certain amount of energy is going to go into anything, and I would argue that that energy in the form of gravity has an equal density of brown and red force, and these little force bits are moving the speed of light. And the idea is when they intersect one of these atoms, they'll either, in the case of the neutral, maintain that percentage. In the case of the negative ion, they're going to become the positive ion. Sorry. This just keeps happening. Stop it! Yes, I'm always well prepared. Obviously. I'm a very good video maker. Anyway. Okay, so the idea would be that the positive ion, because it has less electron and more so the proton's going to be more dominant. So what's going to basically happen to the, well, let's not do what happens in the force until we do this part. So the ion's not going to produce this even amount. In a sense, when the force goes through it or reflects off of it, it's going to create more reds, okay, than blacks, just by circumstance. So it's going to be much more red dominant, and the negative ion is going to be the opposite. Very little red, well, not very little, but more brown. So it's going to have a decided imbalance. I suppose the better way to draw that would be just to do these little lines. So instead of being 50-50, it's going to be more red than brown over here, and this atom would produce more brown than red force, as both reflecting and as transmitting through it. So as the force goes through it, it will come out changed. And likewise, it will reflect more of this red stuff than it will the brown stuff, which it will absorb. So as the atoms are in their free space, let's say, their space inside the atoms, you could sort of just visualize it as there's protons and there's these little electrons. And they sort of end up blending together in the sense that they share these electrons, but they're really separate atoms. So you could figure that there's 5 here and 4 here, or you can think of this as 3 here and 5 here, or 4 here, 5 this way. So in a sense you could make 2 ions here. You could make a 3, and a 5, or you can make 2 4s, 2 neutral atoms. It just depends on how and when you split the atom in two, whether you have the imbalance or the balance. So if you thought about the field, then so now we're gonna hit these atoms with this uneven field. Some extra red is going to come in, or let's say extra black for the sake of this argument, just to make it simpler. So a bunch of extra pressure that bounces off electrons. So it's going to push the electrons, tend to make them want to go this way. So in a sense, if this electron here was going to make a choice, it's getting a little extra push this way. You can sort of see that it's probably going to make the choice to stay with this atom and become a positive ion, than to stay with this atom and be a neutral ion. And because at the same time what's happening is these little nucleuses are moving this way. Just a little bit, but they are. So in this circumstance, you have the electron tending to move towards the proton, which means that's a really a match made in heaven for these two. They like that. They like to get closer together. And here they're doing the opposite. The proton's going this way and this electron's going this way, which is the opposite of the condition more likely to survive. So clearly this is going to be the condition that would survive. The ion's going to move this way. And it's just going to keep happening. Because with each atom, it can keep moving that little electron. Now it's not physically really moving, because all you're doing is pretending there's a difference between this atom and this atom, in a sense, because all you're talking about is a minor bit of separation. In a sense, these atoms are held together by the idea that it would be these 2 electrons would be tied to a proton over here, let's say, and you'd have another electron here that's tied to a proton here. So there could be an atom here. Okay, and this is essentially the bond, is this little odd atom, extra electron. And as stated, it can really just go either way. It can go this way, or it can stay with this one. So the creation of an ion is really simple in terms of it just matters on which way it goes. So obviously, if it's getting pushed by force a little bit this way, this proton's being pushed a little bit towards it. This proton's being pushed a little bit away from it. You can figure this is going to be the ion. The ion's going to move this way. And it just will keep cascading that way. And so that's why it's really moving. This is all force at the speed of light between the proton and the electron. And so the only movement that slows the thing down is this little bit of separation. The moment where you say, yeah, this electron is really this atom's electron versus saying it's this atom's electron. So you make this little subtle decision to it's this atom. Then this side can lose it going this way again. So it makes it permanently this atom when this electron pops out this way, and it goes from being a positive ion back to being a neutral ion. I mean a neutral atom. That's basically what's happening. So you have to understand too that in this circumstance where you have a bunch of these ions are being created, so to speak, by pushing these little electrons are being pushed, but they're not moving very far. But let's just say so you tend to make a whole bunch of positive ions on one side. But the problem with that is the ions, well, these are negative. Oh, it's in the sign convention. So these all repel each other because they're reflecting that force more than they're absorbing it. So they don't like each other. So that ends up being another problem where now you're creating a bunch of things that are hostile to each other. So the positive ions are hostile to each other because they're producing red and reflecting red. The negative ions are hostile to each other because they're producing more brown and they reflect brown. And so there has to be some mitigation between the two. There has to be some mechanism that creates the positive ions, and the negative ions have to have some mixture where they can create a balance that's tolerable. So you're not ripping so the atoms themselves don't get ripped apart and the whole structure of the material would fall apart. So if you had all ions, all positive ions, there wouldn't be any structure. So there still has to be some neutral ions or some negative ions in the right places to keep all of this working. And part of the way that probably works is it just continuously creates what's often called eddy currents and other things is probably part of it. But they just keep switching here. So nobody's a positive ion for very long. And they're mostly negative ions, and they just switch who is going to be the positive ion, just rotates among them. So none of them have to be in the uncomfortable position very long of being the odd man out. But that odd man is very important because that odd man is what's going to hold all of these together and create molecules and structure and all of that. So that's probably enough just to clarify that it's really there's a lot of complexity in this. It's the point I want to make is that the force itself is simple. It's just how much of this stuff is getting radiated by the atoms, the molecules, and then the structure of the whole thing itself. All of those surfaces have a profile of how much proportionally they're reflecting the brown force versus the red force, whether they're positive or negative. And so that's the thing that's dictating. It's the thing everything is, its character is made out of. So its character, its effect, it'll be defined by whether it's producing an even amount of this force or whether it's red bias or brown bias will dictate whether it's positive or negative. And how biased it is will decide how strongly it's producing that bias, how biased the bias is. All right. So, just to say, yeah. So something like this is what's running the system. I'll be that decisive in what I'm saying. I'm pretty decisive about what the force is, that this is the mechanism. The positive and negative components are built into the force itself, and that's the important thing. So the positive and negative component is in the force. It changes the character of the atoms. That changes the character of the molecules. That changes the character of the physical substance. All right, moving on and such. So this is video lecture number 5.
No new concepts, no new ideas. You can relax a little bit. And I want to discuss with you the connection between electric potential and electric fields. Imagine I have an electric field here in space, and that I take a charge Q in my pocket, I start at position A, and I walk around, and I return at that point A. Since these forces are...
Okay, a sort of a thing that has come up is the idea that, just a realization. When they say a charge Q, they're basically saying, okay, I'm pretending we're just trying to detect the gravity. So it's almost like me going into a gravitational field and saying I'm going to put a compass somewhere. I'm not going to put something that's real, something that might affect the other gravitational body. I'm not going to put an Earth next to an Earth. And clearly in this charge scenario, whatever charge you have, how big it is hugely important in terms of how much reflection you create. And certainly what shape it is going to matter, like the infinite plane arguments. So it's a lot more, the truth is going to be more complicated than just saying, well, this is how much radiation the thing is producing. Because key to how much radiation it's producing is, it's just like the ping pong paddle circumstance. I mean, it's fine to take one paddle and just say how many balls are hitting it. But clearly the whole thing really depends on recognizing that the balls are going to come back at a certain percentage. And that's the thing that's really creating the pressure. And so what I'm sort of saying in the previous diagram I did, is that you have two paddles like this. Well, what happens when you insert a third one? They have to do this, to have the same pressure. They just don't have a choice. But anyway, continuing.
Conservative forces, if the electric field is a static electric field, there are no moving charges, but that becomes more difficult, then the forces are conservative forces, and so the work that I do when I march around and coming back at point A must be zero. It's clear when you look at the equation number 3 that the potential difference between point A and point A is obviously zero.
Some stupid U.S. Senate candidate. Ugh, so annoying.
Of E dot dl, and that then has to be zero. And we normally indicate such an integral with a circle, which means you end up where you started. This is a line now. This is not a closed surface, as we had in equation 1.
So it's a little bit confusing, because apparently they have the same sign convention for, yes, closed bag and loop. That doesn't make much sense.
It is a closed line. And so whenever we deal with static electric fields, we can add now another equation if we like that, and that is if we have a closed line of E dot dl, so we end up where we started, that then has to become zero. Later in the course we will see that there are special situations where we don't deal with static fields, when we don't have conservative E fields, but that is not the case anymore. But for now, it is.
Sort of just saying that it's like a hill. You go up the hill, come down the hill. Go up the hill, come. You're in an ideal world. The energy you're getting back by going down is the same as the energy you have to give up going up. So in theory, you're not doing anything. In theory.
So if we know the electric fields everywhere, then you can see equation number 2, then we know the potential everywhere. And so if we turn it the other way around, if we know the potential everywhere, you want to know what the electric field is. And that, of course, is possible. If you look at equation 2 and 3, you see that the potential is the integral of the electric field. So it is obvious that the field must be the derivative of the potential. Now, when you have fields being derivative of potentials, you always have to worry about plus and minus signs. Whether you have to pay MIT $27,000 tuition to be here, or whether MIT pays you $27,000 tuition for coming here, is only a difference of a minus sign, but it's a big difference, of course. And so let's work this out in some detail. I have here...
Unfortunately, yes, mathematics. Maybe I'll speed through some of this. I don't know. You really have to know what all this stuff means, and I don't know what all of it means. It's just basically a way of measuring the strength of the field, and which is useful, but it doesn't tell you anything about what produces it. So Oh, well, we are sped up a little bit. Yeah.
Here a charge plus
Sorry.
Q. And at a distance R, at that location P, we know what the electric field is. We've done that a zillion times. This is the unit vector in the direction from Q to that point. And we know that the electric field is pointing away from that charge. And we know that the electric field E, we've seen that already. The first lecture, Q divided by 4 pi epsilon 0 R squared in the direction of R roof. And last lecture, we derived what the electric potential is at that location. The electric potential is Q divided by 4 pi epsilon 0 R. This is a vector. This is a scalar. So, the potential is the integral of the electric field along a line, and now I want to try whether the electric field can be written as the derivative of the potential.
So the only thing you really get out of that is that it's clearly the charge over R, which just means that the voltage drops in half proportional to the distance. So if you go twice as far away, you have half the voltage. 3 times 1/3.
So let us take the VDR and let's see what we get. If I take this dVdr, I get a minus Q divided by 4 pi epsilon 0 R squared. Of course, if I want to know what the electric field is, I need a vector. So I will multiply both sides, which is completely legal. There's nothing illegal about that, with a unit vector in the direction R. So that turns them into vectors. And now you see that I'm almost there. This is almost the same, except for a minus sign. And so the derivative of the potential is minus E, not plus E. And so I will write that down here, that E.
So all you do is cross those R's out and you got the voltage.
Equals
I mean,
minus
cross out one of the square, cross out the square, and cross out the top R, and then you have the voltage.
dVdr. So they are closely related. If you know what the, oh, and I want this to be a vector, so I put here R roof. Vector on the left side, you must have a vector on the right side. And so if you know the potential everywhere in space, then you can retrieve the electric field. I mentioned last time that the electric field vectors, electric field lines are always put.
So again, the electric field is just a way of saying how disproportional is the energy coming from something in terms of how much red stuff versus how much brown stuff. So if it's 50-50, then it's doing the same thing as gravity, no problem. If it's some other percentage, then for the electrons it'll feel like pressure this way, and for the protons it'll feel like pressure this way, and vice versa. And that's sort of all that's happening here in terms of the mechanics, the simplest mechanics. And everything else is just a complexity of how atoms are structured inside the material. So in a paramagnetic material, they'll do one thing. In ferromagnetic, they'll do another. In conductors and in materials where they can move ions easily, they'll do one thing. In materials where ions can't be exchanged easily or created easily, they'll do another.
Perpendicular to the equipotential surfaces. And that's obvious why that has to be the case. Imagine that you are in space and that you move with a charge in your pocket perpendicular to electric field lines. So you purposely move only perpendicular to electric field lines. So that means that the force on you and the direction in which you move.
So you're moving this way, and there's this change in there's an imbalance in the field going this way, and you move this way, perpendicular. Yet you're going to move with the field lines. I mean, with the field. So I don't know where he's going with this, but we'll see.
Always at 90-degree angles. So you'll only move perpendicular to the field lines. These are the field lines you move.
Right. So you'll only go sideways. I mean, if you have velocity this way, obviously you'll maintain your velocity this way, nothing will change, and all that'll change is, depending on what kind of field you're moving through, you'll move sideways.
Like this. These are the field lines you move like this. So you never do any work, because the dot product between dl and E is 0, and if you don't do any work, the potential remains the same. That's the
Well, you don't do any work because the force is doing it, obviously. I don't do any work if a wave hits me. I don't do any work if wind blows me.
definition. And so you can see that therefore equipotential surfaces must always be perpendicular to field lines, and field lines must always be perpendicular to the equipotentials. And I will show you again the view.
Point is, it's all straight line force. Straight line force. Everything moves in straight lines, so there is no other way to be except moving against a force or perpendicular to a force. Well, I mean, you can have any position, but the only part that's going to matter is the force is going to hit things. The force is going to hit atoms, okay, always at either this way. That's always what it's going to do. It doesn't do tangential reflections. It does. The force either bounces directly off something, or it leaves perpendicularly. That's basically what he's saying, which is completely what my theory predicts.
You graph the overhead projection of the nice drawing by Maxwell, the +4 charge and the -1 charge, the same one we saw last time, only to point out again this 90-degree angle. I discussed this in great detail last lecture, so I will not do that. The red lines are really surfaces. This is three-dimensional. You have to rotate the whole thing about the vertical. So these are surfaces. And the red ones are positive potential surfaces, and the blue ones are negative potential surfaces. That is not important, but the green lines are field lines. And no.
So in some sense, when he's drawing this with the lines going out, which he added to Maxwell, but anyway, the truth is, if you come back the other way, the same rule applies. Force always impacts something perpendicular.
Notice if I take, for instance, this field line, perpendicular here to the red, perpendicular there, perpendicular there, perpendicular there, perpendicular here, coming in here, perpendicular, perpendicular, perpendicular. Everywhere where you look on this graph, you will see that the field lines are perpendicular.
Yeah, so the basic rule is anything you run forward in a physics system, technically you should be able to run backward. And so if you run it backward, it's obeying the same rule, which just basically means everything impacts everything. It does this, a direct reflection, or it does this, but it doesn't do this, and it doesn't do anything else. Right angle or 100-degree angle are the only two. 90 or 180. Those are the only two angles that are relevant
to the equipotentials. And that is something that we now fully understand. The situation means then that if you release a charge at 0 speed, that it would always start to move perpendicular to an equipotential surface, because it always starts to move in the direction of a field line. Plus charge in the direction of the field line, minus charge in the opposite direction. So if you're in space,
the force will always be hitting it that way, and that's the way it'll move. The direction the force hits it at, it'll move at.
And you release a charge at 0 speed, it always takes off perpendicular to equipotentials. You have something similar with gravity. If you look at maps of mountaineers, contours of equal altitude, equal height, if you started skiing and you started at that point and you started with 0 speed, you would always take off perpendicular to the equipotentials. So this is the direction in which you start to move.
You fall off a cliff going down, straight down. You don't fall off the cliff going this way or this way. You go straight down.
If you start off with 0 speed. And now I want to give you some deeper feeling of the connection between potential and electric fields. And I want you to follow me very closely, each step.
So by potential, he's really just describing that if I create these, if I have these two atoms that are tied together, and it can go 3, 5, or it can go 3, 5, you know, in terms of creating ions, or 4, 4. Those are its three choices. He's talking about potential, is that's sort of locked into the potential, is that what these things become. All right, once they become something, this is going to have the yin and this is going to have the yang. So they're sort of tied together in the sense that they have to make all of this difference out of the stuff they have in the box. So until you put something else in the box, this is their potential. It's sort of a reach in terms of saying that's the meaning of potential, but that's sort of the meaning of potential, is what's in the box. And you got to put more stuff in to get more stuff out.
That I make, I want you to follow me. So imagine that I am somewhere in space at position P. At that position P there is a potential, one unique potential, V of P, that's a given. And there is an electric field at that location.
So he's basically saying at that location there's energy coming in, brown and red. And it could have 10 extra reds are coming from this direction, or it could have 5 extra blacks are coming this way. There can be differences in what I'm being affected by. And my system will adapt to that circumstance, and if need be, it'll move in a direction, and certainly everything inside of me will be arranged, okay, to accept that circumstance, to prevent there being little hot spots. It'll take too much energy over here coming in, too much brown will in a sense be spread over everything, and the too much red over here will be spread over everything.
Where I am. And now what I'm going to do, I'm going to make an extremely small step only in the x direction. Not in the y, not in z, only in the x direction. If I measure no change in the potential over that little step, it means that the component of the electric field in the direction x is 0.
Means that there's no change going this way and this way. They're both equal forces. There's just as much red and brown on both sides. Because if you move and you feel more, that means there has to be a source of change. There has to be a difference in one of these directions. You have regular gravity coming in this way, and then you have something changed over on this side. More brown, less red. More red, less brown. So you'll tell that based on the inverse square law, or the r cubed law, or the r law. One of those three laws will tell you, okay, there's a force over there. I mean, there's a charge over there.
If I do measure a difference in potential, then the component, the x component of the electric field, the magnitude of that, would be that little side step that I have made, delta x. It would be the potential difference that I measure.
So again, it's not really an electric field. It's either it's a magnetic field, it's a charge field, or it's an electric field. It's created by any one of those three things. So it's being created by a Van de Graaff or a charged balloon or a magnet. One of those things is changing the field. But the change doesn't say I'm an electric change or I'm a magnetic change. The change is always just an amount of brown and red.
Divided by that little side step. And I keep y and z constant. And these are magnitudes. So that's why I put these vertical bars here. Equally, if I made a small side step in the y direction, and I measured a potential difference delta v, keeping x and z constant, that would then be the component of the electric field in the y direction.
See, by their logic, the magnetic and the electric field are supposed to be separate wave things. You know, one going this way and one going this way. But they tie them together in the sense that they both go out in phase. So when you have something in the electric field, you have something in the magnetic field. So in a sense, they're saying the same thing I just said. You really can't have an electric field without having a magnetic field, and you can't have a magnetic field without having an electric field, because that's the way they work. But the reason why they work that way isn't because they're two separate fields, it's because they're the same force. They're made of the same mechanism as transmitting the information. There's one source of information, two mechanisms for interpreting it.
Earlier, we wrote down for E as a unit newtons per coulomb. From now on, we almost always will write down for the unit of electric field volts per meter. It is exactly the same thing as newtons of coulomb, there's no difference. But this gives you a little bit more insight. You make a little sidestep in meters, and you measure how much the potential changes. It's volts per meters. It is a potential change over a distance. So now I can write down the connection between electric field and potential in Cartesian coordinates. It looks much more scary than the nice way that I could write it down up there when I had only a function of distance r.
So he just means I'll do this three-dimensionally instead of one and two-dimensionally.
And so in Cartesian coordinates we now get E equals minus, that minus sign we discussed at length, and now we get dv dx times x roof plus dv dy times y roof plus dv dz times 0.
Maybe we'll skip some of this math.
And what you see here, this first term here, and this plate is charged negatively. So x goes into this direction. So I can put the electric field inside here.
So he has the A is a minus, the B is a plus. So two oppositely charged plates, that means they're attractive. And he says he has an arrow for the charge, which is, in my opinion, not terribly important. Clearly there's more. There's the 5 ions on one side and the 3 ions on the other side. So you can kind of understand there's a bunch of 3s on one side, a bunch of 5s on the other side. So one's producing lots of the red stuff that the A side couldn't care less about. The A side is creating a bunch of brown stuff that the B side couldn't care much about. Therefore, there's no pressure. The pressure between the two plates is low, and the gravity, the 50-50 pressure on the outside, is strong, because the two inside objects are not sensitive to what the other guy is sending, if you can think of it that way.
According to the recipe, minus 10 to the fifth, and it is in the direction of minus x roof. So x roof is in this direction. The electric field is in the opposite direction, and it's the same everywhere, and that is very physical. We discussed that.
So he has now the electric field going positive to the negative, when, logically you can just say, no, it's really got to be the one that has more electrons is the only one that can change, really. It has to give up electrons, technically. It can't acquire more. It can't become more ionic. So it's just, the convention is wrong.
When we discussed the electric field near very large planes, that the electric field inside was a constant, remember? And the electric field inside was sigma divided by epsilon 0, if sigma is the surface charge density on each of these plates. And we argued that the electric field outside was about 0, and that the electric field outside here was about 0. So it's extremely physical. This is exactly what you see here. Electric field minus 10 to the fifth times x. So the magnitude of this electric field here.
And the 0 comes from the fact that the opposite plate is sending, okay, so the plate facing me is sending me, say, more red than black. The red's going right through me. The black's reflecting. So the 70% red is going right through me, in a sense. And so what's going to end up coming out the other side is essentially going to rebalance what I broke, because I'm only sending I'm sending 70% red out this way. So I'm really just going to put it back to 50-50 going out the other side. I'm going to give it back what it converted. So I'm sending out 70% red. I'm ignoring the 70% that's coming at me because it's irrelevant to me. It's going back through and putting back essentially the 70 I took out. So I made a disproportion that I'm shooting out. It's reflecting back at me. Okay. That disproportion, which goes right through me and converts what's leaving me through my back, is going to be the 50-50, which is the same as gravity. So I'm going to re-equalize the forces going out. I hope you got that. It's kind of important, but I'm sending a disproportion forward by getting the disproportion back, sent back at me. All right, it's basically going to undo what I changed, and going that way, it's going to put it back to 50-50.
The magnitude is 10 to the fifth volts per meter.
And obviously that's true for both sides. So both sides are doing exactly the opposite change, and both are getting reflected back at them what they changed, and therefore both will produce exactly a reflection that looks just like gravity. So obviously it won't have any magnetic or electric meaning.
What now is the potential difference? Well, VA minus VB is the integral going from A to B of E dot dl. Well, I go from here to here, so I write down for dl, I write down dx, of course, because I call that the x direction now. So I will write down here dot dx. And so this is minus 10 to the fifth times the integral and going from A to B.
So just quantifying the voltage potential between these plates, which will always be based on how close they are and how dense the ions are. The negative ions versus the positive ions.
Of x roof dot dx. Looks scary, but it is trivial. X roof is the unit vector in this direction. And dx is a little vector dx in this direction. So they're both in the same direction. So the cosine, the angle between the two is 1. So I can forget about vectors, I can forget about the dot.
Just pointing out that if the two plates are parallel, everything has to go in straight lines, so you don't have to worry about measuring non-reflections and all that kind of stuff.
So this becomes
The
minus
stuff that escapes.
10 to the fifth times the integral in going from A to B of the x. And that is trivial. That is minus 10 to the fifth times the location. I have to do the integral between A and B. So I get here x of B minus x of A. And if this is 10 to the minus 2 meters, to go from here to here is 1 centimeter, I must multiply this by 10 to the minus 2. So I get that this is minus 1,000 volts.
So he has 1 centimeter for a charge of, I guess it's a charge of 1 and charge of 1. So A and B are Q's are being considered 1, I guess, for the sake of this scenario.
So A is 1,000 volts lower than B. That's what it means.
Okay, so it's just a relative comparison, but it still has to be a relative comparison based on two equal charges. So one is a minus 1 and one is a plus 1. Okay, there. Better way to say it. And so your expectation would be this much, 1,000 volts per centimeter would be created if you took two plates that were stuck together that somehow you could maintain the fact that they were, this plate was all more negative, plus one of negative ions in terms of density, and this one was plus one of positive ions in density. And you didn't really touch them or whatever, and then you move them, okay, against their will, okay, from this position to this position, you'd end up with 1,000 volts. Theoretically, if you move them to this position, you'd end up with 2,000 volts.
And that's something that's very physical. Notice that if you go from left to right, that the potential grows linearly. This is lower than that. And if you, in your head, use planes like this, parallel to the other planes, each one of those planes would be equipotentials. They everywhere have the same potential. And gradually when...
Yes, so you could put a bunch of others in here, and you could put one down the middle, and then you'd have 500 volts and 500 volts. And then you could put two in here, and then you could have 250 volts, 250 volts, 250 volts, 250 volts. Then you could just keep putting planes in and cutting the voltage each time.
You move it up, your potential increases. But notice the electric field goes from plus to minus, in the opposite direction. That's always the reason that's behind that minus sign.
Yeah, I think these directions just add confusion. The voltage and the current really are going in the same direction. It just has to do with how when the conductor is charged, and after that it's really is the voltage is reversed. I mean, what you think is the low end is really the high end, blah blah blah.
Well, clearly I'm always free to choose where I choose my zero potential. We discussed that last time. You don't always have to choose infinitely far zero. So I could choose this arbitrarily to be zero potential. This would then be plus 1,000. And so you then...
So then he would be saying this is that this B would then be a 2 charge, then I would argue, right? It would have to have twice as many ions, negative ions, if the other side is neutral. Or what's he saying? No, he's just saying the relative difference is always 2. That's all. So make it 0, then the other one is a plus 2.
Find that the potential V is then simply 10 to the 5th times x. When x is 0, you find the potential to be 0. And when x is 1 centimeter, you find the potential to be 1,000 volts. And that then goes together with the electric field equals minus 10 to the 5th in this direction. And so this is extremely physical. This is something that you would have whenever we deal with parallel plates. As long as there's no charge moving, and we're dealing with solid conductors, so we have static electric fields. Charged.
So let's just understand, there's probably not, you can't do that in an atmosphere in perfect circumstances. You really can't have fields that are static because the atmosphere is draining them to some extent. So they are moving a little bit.
If they're not heavily moving, then the field inside the conductor is always 0. Not the case in a non-conductor, only in a conductor, because conductors have free electrons to move. And if these free electrons see electric fields inside, which they may, they start to move until they experience no longer a force, thereby they...
So again, he's saying that's what they're doing, that they're somehow sensing the charge inside and da-da-da-da. When all they're really doing is, as I pointed out, they're reflecting. So everything gets back what it produces in some sense if it's the same charge. So it's just that argument, okay, the through argument. So on the outside, just as he pointed out, on outside of those two planes, it's 0 on the positive side and it's 0 on the negative side. Both of them end up with nothing. And you can just think of that as being the inside of the surface if you made something that was spherical. Just trying to think of how to draw that, but we'll wait.
Kill the electric field inside. So the charge in a conductor always rearranges itself so that the electric field becomes...
See, I don't think that's really what's happening. It's just that argument of the gravity argument, that no matter where you move in the field, it will be equal amounts of of force. But it's really not the same. See, the gravity argument's depending on the fact that when you move, you expose yourself to more stuff behind you. You know, it's this cone argument, this intersecting cone. So wherever you move, if you get closer to a surface, the cone gets smaller. As you get further away, the cones get wider. At the middle, the cones are equal in both directions. So you can sort of understand that you're just changing how much you're exposed to and how far away it is, and that'll be exactly equal to the opposite of the other side. In this case, there's no opposite forces to oppose. They've all been neutralized to 50-50 by the rules of the interaction in the plate. You know, the other plate is reflecting back at you.
0 if the field is a static field, not rapidly changing. And so now I want to evaluate with you the situation that I'm going to charge a solid conductor and ask myself the question.
Okay, I don't know if this is true, a true way to look at it, but in a sense you could say, probably cheating in some way, that the two surfaces of the metal are essentially creating two plates, and that on the opposite sides of the plates there isn't anything happening. But clearly on one surface you're going to have charge, so that doesn't exactly fit. Yeah, so forget about that one.
Where does the charge go? In honor of Valentine's Day, let's take a solid hard, steel hard. It's solid all the way throughout. So this is a solid conductor, and I bring on this conductor charge from the outside. Plus or minus, let's just take plus for now. And so the question that I'm asking you now, this is a conductor, this is not an insulator. The story for insulators is totally different.
So he's put a bunch of negative ions, right? Well, negative ions would be ones with extra electrons. Oh, geez, see, this is so bad. So he's put positive ions on there, right, to match the positive, which means they're the small atoms with they're missing electrons.
This has free moving electrons inside. I'm asking you now if I touch...
See, that's the whole point. It really doesn't. If it's got a bunch of negative ions, it's short of electrons. It's saying, I wish I had more electrons.
This conducting heart, by the way, your heart is a very good conductor. If you touch this conducting heart, where would this charge end up? Where would it go to? And I leave you with 4 choices. And we'll have a vote on that. The first choice is that the plus charges would uniformly distribute throughout. The possibility.
Well, I don't know why they wouldn't. So he's saying where would the charge go, or does he say he's putting another charge on there? So putting the charge on, obviously it's a conductor. It's going to spread across the entire surface.
The second possibility, less likely I think, that all the charge will go to one place there. I don't know which place that would be, but maybe. And then the third possibility is that maybe the charge will uniformly distribute itself only on the outer surface.
All right, now, so there's a subtle difference. So he's saying one thing would be the charge goes through see, this is where it just gets technically a little strange. Because now what he's saying is it's not a hollow surface, it's a solid surface, but essentially a solid surface doesn't matter. It's going to do the same thing. The solid surface is going to have the same problem the interior surface had before, in the sense that it's already going to be neutralized. So there's not going to be anything on the inside, whether there's material on the inside or not. The whole point is that the inside ends up neutral.
And then the fourth possibility is none of the above. All these suggestions I made were wrong. Who would think that the charge might uniformly distribute it throughout the conductor? I see 1 or 2 hands. That's good. Don't feel ashamed of raising your hands. In the worst case, you're wrong. I've been so many times wrong when it comes to this.
He always kind of gives away the answer. So he's basically telling them, nah, you fucked up. Wrong.
Don't feel bad about that. Who thinks that the charge will all go to one point in the heart? You have the courage?
He wants to just laugh at this guy. You know, what are you thinking? What? I just told you it was a conductor, idiot. How could it possibly go to one spot, you moron?
You think it will go to one point? Charge repels each other, right? But that doesn't seem likely. Who thinks that it will uniformly distribute itself on the outer surface? Who thinks none of the above? Very good. Well, those who suggested that it might be uniform on the outside, I would still give them a B, but it's not uniform, as you will see. But it will go exclusively to the outside, and I will prove that now to you. Let us first look for that ridiculous possibility that the charge would somehow end up in the conductor itself. I take here...
All right, so the catch is... So this is kind of complicated. So if you're saying the charge is on the outside, then the problem is you have, wherever you have an indentation in the surface, something that goes into the sphere, you're going to have a problem where those charges will be repulsive now, and you know, there are going to be less of them there because they're going to repel each other because they're in closer proximity than they would be if it was a sphere. So yeah, so there'll be some unevenness in the external charge because there'll be some unevenness in the surface charge.
Here, a Gaussian surface, which is a closed surface. I know inside the conductor, if we have electrostatic fields, not fastly moving charges, but it's a static field, I know that the E field everywhere must be zero on the surface. This is a closed surface. So the integral of E dot dA, equation 1 is 0. That means the charge inside my sphere is 0, and so there cannot be any charge. So Gauss' law immediately kills the possibility that there would be any charge.
Sort of a conservation argument, I suppose. How else can you look at it? You know, obviously, if the charges want to get away from each other, especially if this is really heart-shaped, that is, it's a shape like this with a cut in it. Obviously, the charges on the two sides really don't like each other, and anything caught in between them would be, you know, it would sort of be saying, go over here or go over here, but you can't stay here. Okay, I mean, we're repelling you. You got no business being in the middle here. I mean, this is repulsive, this is repulsive. It's saying get the hell out of there, basically, right? It's saying go to the surface where there's more room. You know, you can, you know, you can fly with the birds or something. You can, you know, gain more space out there than you can in here.
Inside this conductor. So that's out of the question. So that leaves you only with one choice, that is at the surface. The charge must be at the surface. And later, in a later lecture, I will discuss with you.
But the point is, this stuff still has to be made out of something. So all of this, all of this talk about moving atoms, flying out of stuff, they all can't go to the surface. And obviously the atoms that are negative ions are going to be attracted to the ones that are positive ions, and so they're going to make chains.
The details why that charge is not uniformly distributed. It would be uniformly distributed at the surface if this were a sphere, but not if it has this funny shape. But it will be at the surface. Now, I'm going to make this heart a very special heart, more like a real heart. It's open here, but it is solid here. So this is a conducting, the heart muscle, and here it's open. There's nothing here. And again, I'm going to charge it. Bring charge on the outside. So now, it's obvious that we don't expect that there is any charge that will be inside the conductor. That's clear. The same argument holds with the Gauss law argument. But now, is it perhaps possible that some of the positive charge will go on the inside of this surface and some on the outside? Who thinks that maybe some will now go on the inside, because now the situation is different, right? It's now a hollow conductor. Anyone in favor of some of that charge?
It's really not a hollow one, frankly, but it's still full of some kind of material, so it's not purely hollow.
Maybe going on the inside. See, one hand, two hands. Who says, no, it's not possible, it will not go to the inside. It will still go to the outside. Well, most of you are very careful now, you don't want to vote anymore. It cannot go to the inside. Why can it not go to the inside? Let this be my Gauss surface. closed surface.
See the Gauss surface doesn't really explain to you why it can't go to the inside. It doesn't give you the mechanics of why the atoms won't create an ionic surface on the inside, a prejudice. And again, but my argument would be the prejudice is built in to the fact that it's to create an imbalance is the yin-yang thing. So there's somewhere there's a yang for the yin on the outside, and that has already balanced the conductor itself on the inside. It has to be restorative somewhere. If you put all that positive on the outside, you have to be putting negative somewhere else, and the two of them will add up to the same thing you had before, 50-50. You always have to end up with the 50-50 somewhere. Well, no point in me just saying that, because I have to explain why that has to be, but it really has to be by the fact that you're introducing, even though you introduced these ions, yes, so you introduced ions, the system is going to react to that by creating the opposite circumstance. It's going to put more ions somewhere else, the opposite, to meet those. So yeah, they're going to be next to. Yeah, the negative ions are going to be intimately involved with the positive ions, because it's not like you're still in the field. You've placed charge on. See, this is where it gets so, you have to be so careful. See, it's one thing when you place this thing in an electric field, for example, and you are talking about what's happening. And it's another thing when you've got it in a clean field and you just put charge on the surface. Those are two different experiments. So anyway, you got to keep that straight. All right, anyway, that's probably enough for this video. So we will see you next time and such. Thank you for your attention. Comments relevant to the subject matter would be appreciated and such.